Control of corrosion under thermal insulation and fireproofing materials. A systems approach integrated strategies to prevent corrosion in insulated systems. Introduction to corrosion under insulation and fireproofing. Corrosion under insulation (CUI) and corrosion under fireproofing (CUF) represent two of the most challenging and costly degradation mechanisms affecting industrial assets, particularly in the oil and gas, petrochemical, and power generation industries. These forms of corrosion occur when moisture becomes trapped between insulated or fireproof materials and the underlying metal substrate, creating an environment conducive to corrosion processes that often remain hidden from view. Because insulation and fireproofing are designed to protect equipment from thermal loss and fire exposure, they unintentionally obscure early signs of corrosion, allowing damage to progress undetected until leaks, failures, or safety incidents occur. CUI and CUF are especially problematic because they are influenced by a complex interaction of factors, including operating temperature ranges, insulation type, environmental exposure, material selection, and maintenance practices. Carbon steel, low-alloy steels, and certain stainless steels are particularly vulnerable under specific temperature and moisture conditions. The economic consequences include unplanned shutdowns, repair costs, loss of containment, and increased safety and environmental risks. This presentation introduces a systems-based approach to managing CUI and CUF, emphasizing that no single mitigation measure is sufficient on its own. Instead, effective control requires coordinated consideration of design, materials, coatings, installation quality, inspection, and ongoing maintenance throughout the asset lifecycle. By understanding CUI and CUF as systemic integrity threats rather than isolated issues, organizations can implement more robust, proactive, and sustainable corrosion control strategies. Fundamentals of CUI and CUF: damage mechanisms and contributing factors. The damage mechanisms associated with corrosion under insulation and fireproofing vary depending on material type, operating temperature, and environmental conditions, but they generally include uniform corrosion, pitting corrosion, crevice corrosion, and stress corrosion cracking. Carbon steel commonly experiences general wall thinning and localized pitting, while austenitic stainless steels may suffer chloride stress corrosion cracking when exposed to chlorides leached from insulation materials or marine environments. These mechanisms are accelerated when insulation systems absorb and retain water, creating persistent wet conditions at the metal surface. Key contributing factors include water ingress from rain, washdowns, condensation, or process leaks, combined with temperature ranges that promote evaporation and concentration of corrosive species. Certain temperature bands, typically between approximately -4 degrees Celsius and 175 degrees Celsius, are especially conducive to CUI due to repeated wet-dry cycles. The type and condition of insulation or fireproofing material also play a significant role. Damaged jacketing, poor sealing, and degraded fireproofing allow moisture penetration and retention. Environmental exposure further exacerbates the problem. Marine, coastal, and industrial atmospheres introduce chlorides, sulfates, and other contaminants that increase corrosion rates. Without systematic controls, these factors interact to create high-risk conditions that can rapidly degrade asset integrity. Understanding these mechanisms and contributors is essential for developing targeted prevention, inspection, and mitigation strategies within a comprehensive CUI/CUF management framework. A systems approach to CUI and CUF control, life-cycle-based corrosion management. A systems approach to controlling corrosion under insulation and fireproofing recognizes that effective prevention and mitigation must span the entire asset lifecycle, from initial design through operation, inspection, and maintenance. Rather than relying solely on inspection to detect damage after it occurs, this approach emphasizes building corrosion resistance into the system from the outset. Design decisions such as equipment layout, insulation detailing, and drainage provisions can significantly reduce the likelihood of moisture accumulation and corrosion initiation. Material selection is another critical system element. Choosing appropriate alloys, coatings, insulation, and fireproofing materials based on operating conditions and environmental exposure helps ensure compatibility and long-term performance. Protective coatings, when properly specified and applied, act as a primary barrier against corrosion. However, their effectiveness depends heavily on surface preparation, application quality, and inspection prior to insulation installation. Installation quality and workmanship form the next layer of defense. Poorly installed insulation systems, damaged vapor barriers, and improperly sealed penetrations undermine even the best design and material choices. Once assets are in service, inspection and maintenance complete the system by providing feedback on performance and identifying areas where controls have failed. Risk-based inspection methodologies, combined with targeted non-destructive testing, allow resources to be focused on the highest risk locations. By integrating all of these elements into a coherent management system, organizations can more effectively control CUI and CUF risks, reduce lifecycle costs, and improve safety and reliability. Inspection strategies and ongoing mitigation. Inspection and mitigation are essential components of a comprehensive CUI and CUF control strategy, providing assurance that preventive measures remain effective throughout the operating life of an asset. Because CUI and CUF are often hidden, inspection strategies must be carefully planned and risk-based. Risk-based inspection (RBI) methodologies help identify susceptible equipment by considering factors such as operating temperature, insulation type, environmental exposure, and historical damage data. This allows inspection efforts to be prioritized where the likelihood and consequence of failure are highest. A combination of inspection techniques is typically required. Visual inspections of insulation systems, jacketing, and fireproofing can reveal damage, gaps, or signs of water ingress. Non-destructive testing methods such as ultrasonic thickness measurement, radiography, and infrared thermography can be used to assess wall loss and detect moisture without full insulation removal. In some cases, selective insulation removal is necessary to directly examine the condition of the substrate and coatings. Mitigation activities focus on addressing identified deficiencies and preventing recurrence. These include repairing or replacing damaged insulation and fireproofing, improving sealing and weather protection, reapplying or upgrading protective coatings, and correcting design or installation issues that promote water retention. Equally important are organizational best practices, such as maintaining accurate documentation, training personnel on CUI/CUF awareness, and integrating corrosion management into broader asset integrity management systems. Together, these practices support a proactive, disciplined approach that minimizes the likelihood of unexpected failures and ensures long-term asset reliability.